start recording. So let me check. My audio is on. I can see it right here. I see I'm sharing and I am recording. Now I have to triple check to make sure everything is okay. So let me go back to the slide where I wrote start here. Okay, so real quick before I start, do you have any questions about lecture, lab, any information before I continue? If you can't think of any, if you cannot think of anything right now, but you think of something later, even if it's during the lesson, just go ahead and type it in. That way, whenever I'm done or I get to a stopping point, I can go ahead and just read it and address it. Okay? Okay, so I guess I'll start here. Oh, the degenerate. Okay, so degenerate. Now, do you want me to go over the quantum number as far as the degenerate is concerned, or just the degenerate orbitals in general? Let me see. And while you're doing that, let me go ahead and grab my picture. Because I think last time I talked about two things in general. You're talking about, because when I think of degenerate, a lot of things come to mind for me, right? I have to modify my quantum numbers for carbon, nitrogen, and yeah, for carbon and nitrogen because of the degenerate orbitals. And then the other thing I think about with degenerate is Hund's rule. So let's see. Let me find that periodic table I had here. That's the two things I can think about. So I'm going to talk about that. And if I haven't answered the question you have, then you want to go ahead and ask it differently, right? So I know how to answer it. Okay. So this picture right here shows us the sublevels, right? So I'm going to need my picture in my new section I'm discussing. Let me go ahead and erase this so I like it a little bit cleaner and then copy it. Copy. And I can scroll down to where I was. So let's see, where does it say start here? I'll just add a slide. Yeah, degenerate occurs because we have many electrons. Okay, so right here, we have many electrons in an orbital. So what I'm going to do is on slide 61, I'll add a page and then we'll go from here. Okay. So as we're looking at this slide here, what we're seeing is the sublevels, right? I didn't make this slide or this picture, but I found it online. But if I were to title this, I will do more than just write electronic configuration in the periodic table. Yeah, it is this slide or this this periodic table can be used for electronic configuration, but that's not what it's really showing. What it's showing us here is the sub levels, right? Remember, the energy levels are the, N is equal to 1, the energy level very close to the nucleus. And then we have N is equal to 2, and N is equal to 3, all the way to, as far as the periodic table is concerned, the highest N value we see is when N is equal to 7, right? So N is 3, and this goes all the way to N is equal to 7, right? These are the energy levels. But because the atom has got many electrons, so we wish it was this simple, because this is how Bohr described the energy levels, that the energy levels were continuous and they were not broken down into sublevel. But instead of having a continuous energy level, the reality is we have sublevels, okay? So instead of having continuous energy levels like this, we have sublevels. So I kind of wrote it opposite to what we normally see it as, okay? So let me stick with the natural convention. In the natural convention here, let me see. The labeling is opposite. They tend to have the lower energy level on the bottom. I don't know why. I guess they like showing it this way. So the nucleus will not be on the top. The nucleus will be on the bottom because the nucleus tends to be very close, or the nucleus, let me spell this correctly, is next to energy level 1. Okay, so you have your nucleus here. This is the side of the nucleus. And the energy level increases like this. So energy level 1, energy level 2, energy level 3, energy level 4, and it goes all the way to energy level 7. Okay, so we're not a degenerate yet. I'm trying to build towards that. instead of having connected energy levels like it shows right here, the way Bohr said it was, in reality, when we get to energy level 2, the energy level begin to split. So instead of having a continuous energy level like this, we have energy level broken into pieces, and those pieces are called sublevels. So on energy level 2, you have two pieces of the energy level. The lower one is called 2s. They're all still from energy level 2, but they're broken into what we call sub levels. So 2s, and then we got 2p. And then for energy level 3, instead of having a continuous straight energy level where all the parts of the energy level are the same level, now we have sub levels. So I'm beginning to see I should use different colors. So just so that we can follow along, I'll label energy level 3 a different color. How about blue? Energy level 3 will be shown in blue colors. So for energy level 3, we have 3s, 3p, 3d. Energy level 1, we only have one level. Energy level 2, we only have we have two sublevels. Energy level 3, we have three sublevels. And energy level 4, instead of having one continuous energy level, we have four sublevels. Now the four sublevels used to be one level, but they broke up into different levels because there's so many electrons. So the many electrons, the multi-electron situation is what causes this to exist. Okay. So let me choose a color for energy level 4. Let's see. I'm only going to go to 4, even though we know the energy level goes to 7. How about purple? So energy level 4 is going to be illustrated by purple color. So I'm going to show here 4s, 4p, 4d, and then 4f. I'm running out of room. Now the way I showed it here is kind of, yeah. Technically, let me adjust the 3D here because in order 3D is actually behind 4S. So let me redraw 3D a little bit up here. It's slightly above 4S. Okay, so now we're talking about the orbitals because the orbitals are the ones that are degenerate. Okay. So to talk about the orbitals, let me adjust this so it's consistent with the size. Energy level 1, remember, has only one energy level, and that's now called 1s to fit with everything else. So in the sublevels, we have orbitals. Now I mentioned this before. Holistically, do I have room? Let me write it over here. For each S sublevel, we'll only have one orbital. For each P sublevel, we'll have three orbitals. For each D sublevel, we'll have four orbitals. For each F, sorry, not 3 and 4, 3, 5. My brain defaulted back to counting. So it's 1, 3, 5, and then 7. So it increases by 2. Okay. So in each of these sublevels, you have the following number of orbitals. Okay. So before we explain degenerate again, remember, each of the S's, regardless of the energy level, only has one orbital. So I'm going to go through here. And in the orbital diagram where we talk about degenerate, the orbitals are shown as boxes. So I'm just going to kind of give you a little clue here. Orbitals drawn as boxes. Okay, so each orbital is one box. So I'm going to go through here and draw one box which represents one orbital for all the s's, okay? Because it says here, each of the s's only has one orbital. So I put a box here. Now I put a box here also, right? Because all the s's must have one box. To be consistent with the color, I put one box here. And then to be consistent with this color, I put one box here. Regardless of the energy level, all the S sublevels or the S orbitals have to have one box. Okay, so hopefully that's clear. So I am done showing you this part. I'm now going to be moving to the P's. The P's have got three orbitals in the P sublevel, regardless of the energy level. Okay, so I'm going to start with red, I guess. And that's when you have the whole degenerate, right? 1, 2, 3. So every whether it's 2p, 3p, or 4p, has three orbitals, right? So let me go through and then finish the electrons. Then you see how this works out. So let me see. What's the next color? Blue. One. How did I pick blue and end up red? Okay, maybe I didn't touch it enough. There. Okay. One, two, three. So you see how I'm drawing the orbitals side by side? So the side by side orbitals that are kind of connected, like connected segments, these are called degenerate. Okay. And then this one here, this by side like that connected, these are degenerate. So I'm just going to use this to say these three like right here, these are degenerate p orbitals. Okay. What makes them degenerate? You have more than one orbital on the same energy level. They're all on the same level, kind of like a shelf, right? And they're all at the same level. One isn't higher than the other. Even though I may have drawn them lopsided, technically they're all on the same energy sub level, and that's what makes the orbitals degenerate. Okay. Right. So when I go to the four, even though I have these fours right here, with the D, I have how many? Five? That's what we said right here. D's have five. So one, two, three, four, five. These are also degenerate. They're just degenerate d orbitals, right? Because degenerate just means orbitals on the same energy level. It would be like orbitals on the same shelf. They're all the same energy level. One isn't higher than the other. You cannot say S and P are degenerate. These are not degenerate because P, you can see, is higher than S. So those are not degenerate. And the way Bohr showed things before, that's why you see now we have a better model. Bohr made the whole energy level degenerate, but it wasn't that way. These are actually at different levels. Where was I? So with this D, the purple D that we have right here, once again, we'll have five orbitals. I'm glad you asked this question because when we get to that one chapter, I forget what number it is, where we're going to be doing degenerate stuff, this part will become very important, right? Because we're going to come back to this quantum stuff and look at all these orbital diagrams. So over here, I have one, two, three, four, five. When we come to the D orbital, we have degenerate D orbitals. Only this time, we have one, two, three, four, five degenerate orbitals. Then with F, I can't even draw it over here. F, we have seven degenerate orbitals, okay? So what can we conclude here? Because the S block, the S sublevel only has one, what we can conclude here, holistically after looking at this, is the S orbital is not degenerate because we only have, oh, I'm running out of space, because we only have one orbital. The prerequisite for degenerate is one orbital. It has to be, so it has to be more than one orbital, and they have to be at the same energy level. Okay, so hopefully that is clear. Yeah, I see that Victoria has some connectivity issues. It's easier to just log out and then try to log back in. I don't know what the issue is. It's Friday afternoon in the world of Collaborate, but sometimes you have to do that. Okay, so now that we've seen all the degenerating, and remember I mentioned this last time, I think we went over how to form ions and everything. Once again, if you guys have questions in your homework, have you guys gotten all your homework questions done? Or your quiz questions done or anything? Okay, let's do this. Let's finish the chapter, and then that way, if there's any homework questions that you can think of that maybe you had a question on, we can go over that after we're done with this part here. Okay. So now we are looking at periodic trends. So the thing with periodic table, because this chapter in a way has us examining the periodic table as a whole, one of the things we use with the periodic table is to use periodic table to study behaviors, right? Remember when we started learning about quantum numbers, we said our rationale for studying quantum numbers is to learn the behavior of the elements. So now we use the periodic table to study trends. So there are trends of the atom behavior. So we're going to be looking at very specific behaviors that we see in the atoms/elements that are periodic, meaning they're very trendy, right? As you go from left to right. And then most of the time, I'm just going to give you the summary. When we look at the periodic table, the more direct observation we have is from left to right or right to left, and then up to down or down to up. That's the most basic observation we usually make in the periodic table. When somebody tells you observe a trend, you kind of have an idea of what they're saying you should do. They're telling you look from left to right. Do you see a familiar pattern? Are you seeing any pattern from left to right? Something that you can make a generalization from. Or look at top to bottom. So my teachers weren't exactly very clear about this when they were doing this in school. A good thing is I got to see this at some point towards the end of middle school, high school, then in college. So at some point I realized, wait, we've been here before. I said to connect periodic trends with looking left to right, top to bottom. At first I was like, I'm lost. Where are we looking again? And then there was no PowerPoint, y'all. The struggle was real. But I'm just telling you, in general, periodic trend means look left to right. Do you see a familiar pattern? So we're going to start with atomic radius. Scientists noticed there was a connection between the radius, the radii, and the position of the atoms in the periodic table. So let's start with the overgeneralization, right? The trend. What is the observation? The observation here is atomic radius decreases across the period from left to right. Okay, so as I read this, oops, I'm trying to erase this. What did I click on? As I read this and add a page, let me add a page down here. I want to connect with it just a little bit more. So I'm going to draw myself a mock periodic table and then try to illustrate this so I can connect with it a little bit more. Atomic radius decreases across the period from left to right. Okay, so I'm going to draw myself a mock periodic table. My simplified periodic table is usually very, very simple. Okay, it looks more like a rectangle sitting on its longer side. And they're saying here, if you're going from left to right, the atomic radius decreases. Since the atoms are circular, they're trying to say that you should have your biggest atom on the left, and as you go right, it gets smaller, 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 smaller. Okay, that's what I'm getting from what they're saying. From left to right, atomic size or radius decreases. Okay. And then I'm going to read the overview first before I go into the why. And then they say atomic radius increases when you go down the group. Down the group is down the column. That means, oh, I should have made this a little smaller. As you go down the group, this size gets really large. So I'm just going to start with 3, right? So from top to down, this increases. Okay. So this is what they're saying, right? Now I went from being the student that got so stuck on the details. I still do that, and it took me a while to learn the bottom line. So the bottom line is this: compare this size, right, to this size. If you were to even generalize the more, right, where would you say the smallest atom is in the periodic table based on the picture I just drew here? Where is the smallest and where do you think the largest is? This is a picture I drew, right? So I look at this and I'm thinking from the picture I drew right here, smallest is top and right, right? So if you look at the top right of the periodic table, you should find the smallest element. And if you look at if you look at diagonally opposite from it or bottom left, you have the largest. This is not 100% true because if it was, chemistry would not be a mystery, right? But it's about 90% true, okay? So because the noble gas elements are right here, and for most of our periodic trends, we leave them out, if you just went from the left all the way to group 7, let me see, where's my periodic table? I had it somewhere here. Yeah, so if you ignored this group right here, that trend will be true. Fluorine will be your smallest element ever in the periodic table if you ignore these. Okay? Fluorine is the smallest element. These here slightly get bigger. Once they get stable, they slightly get bigger. And so you have a decrease. So going from lithium to fluorine, the size decreases, decreases, decreases. And by the time you hit hit fluorine atom, you have the smallest atom. Okay. And then going down the group, the size increases, increases, increases. By the time you hit francium, you sort of have the largest size atom, but when you do experiments, you actually find out that in some cases, sometimes francium is not necessarily the largest. Cesium ends up being the largest. So these trends are called general trends because within the trends you have exceptions. So please notice that these are general trends. I'm going to write here, these are general trends. In chemistry, when they use the term general, they're saying that this is most of the time true, but it's not 100% of the time true. So in general, when we go from left to right, the size of the atom gets smaller. In general, when we go from top to bottom, the size of the atom gets bigger. Of course, there are exceptions to every rule in chemistry, and so we will see the exceptions. Okay? So this is essentially the general trend. So you want to be able to recreate that. Okay. Now, why is the atom getting smaller when we go from left to right? We're going to be looking at the why. They tell us here, because apparently adding electrons to the same valence shell causes the size to get smaller. So these are the 3 bullet points that explain what's going on. Adding electrons to the same valence shell, okay. Effective nuclear charge increases, okay. Valence shell is held closer, okay. What does that mean exactly? Let's go ahead and examine these statements here. So we're going to take this to the next page and examine it. So I'm going to give you guys more generalized rules because when I read stuff, I like rules. And when they're not rules, I make up my own rules because it helps me to mentally focus on the point and help me get to answers. So based on these statements they made, okay, based on the statements they made, I gather that apparently the way the valence shell is held determines the size. Now, that wasn't mentioned here. It's implied when you read the whole, all the statements in this slide. Okay? So this is the bottom line. Bottom line. Attraction between the nucleus, remember the nucleus is positive, right? The nucleus has a positive charge. So attraction between the nuclear positive charge and the valence electron. Remember, the valence electron is the one on the outer energy level, the one that's the nosebleed section. It will be like the last electron that actually got assigned to the atom. So this is the one on the valence level, very, very far from the nucleus. So the attraction between the nucleus and the valence electron, that is, remember, negative charge, determines the size of the atom. Okay, this is the bottom line. So I'm trying to write out in words what our metrics will be, what we're going to be using as a means to judge, is this atom big or is this atom small? Okay. In other words, we're looking, so once again with me, I'm like, yeah, I see words, but I need a picture. Can we make a picture out of this? Sure. This is our atom, and this is our nucleus, and this is positive. Then the outermost electron is very close to, it's still in the atom, it's just not out, but it's out here. So we're saying the nucleus is attracting the electron to itself. The power with which the nucleus pulls the electron determines the size of the atom. So anything we do to make the positive more positive makes the suction power even greater or the attraction power even greater. Anything we do Right. Once again, so whatever we do to make this positive more positive will make the electron be pulled even more. Okay, so this will apply later on when we talk about removing electrons and ions, and it gets into all of that stuff. But for right now, remember, bottom line, nucleus attracting negative electron. So then they say here, adding electrons to the same valence shell. Okay. Remember, the valence shell is that row very close to the edge. I mean, like the rim of the atoms. We'll call this the valence shell. So what they're trying to say here is, I'm going to use carbon, nitrogen, and oxygen. Okay, I'll use these right here. These to explain what's going on. Okay, carbon, nitrogen, oxygen. I could use fluorine too, but those three are okay. So these elements are side by side with carbon, nitrogen, oxygen. Carbon has atomic number of 6. Nitrogen has 7. Oxygen has 8. What does that mean? That means the nucleus of carbon has positive 6 charge. The nucleus of nitrogen has positive 7. The nucleus of oxygen has positive 8. Okay? Now, each of these also has the same number of electrons. 6 electrons, 7 electrons, 8 electrons. We don't really care about all the electrons. We care about the outermost electron. Okay, so this is a nucleus, and then we're looking at the outermost energy level. In the outermost energy level, let's see, how does this work out? We have energy level 1 that just has 2 electrons. I'll draw them as X's, energy level 1. Energy level 2, I'm going to keep this simple. All of energy level 2 has how many? Was it 8 electrons? Energy level 2 has 2 here. 1, 2 here. 3, 4, 5, 6, 7, 8. Yeah, energy level 2 gets all the way to 8 electrons. But on this one here, since I placed 2 here, I should have 4 remaining. So I have 1, 2, 3, 4. So I can pick any of these electrons on energy level 2 and try to get it attracted to the nucleus. So you see here, the nucleus of positive 6 charge is trying to attract this electron on energy level 2. So going from carbon to nitrogen, how does this picture change? I need to space this out a little bit. I do this a little too close. How does that picture change? Well, in the case of nitrogen, the 5th electron, so see right here, right? This is what we expect to have. 1, 2, 3, 4. 1, 2. Energy level 1 has 2 electrons. Energy level 2 is supposed to have 5 electrons, right? 1, 2, 3, 4. When I put 4 electrons in energy level 2, it matches carbon. But when I put the 5th electron here, this now makes this structure here nitrogen. What happens? The fifth electron on energy level 2 is being sucked into the nucleus by a stronger charge. So this one here, valence electron attracted by a nucleus with plus 6 charge. Okay, this is pretty strong. Plus 6 is strong. But with nitrogen, the last electron, which is this one here that I put in, this is our last electron here, valence electron attracted by a nucleus with a plus 7 charge. Okay, remember I told you anything that makes the charge stronger, bigger, makes the attraction stronger. So between these two, you can see the nucleus in nitrogen has greater, I like to call it sucking power, because I feel like the nucleus is just sucking the electron like, a vacuum with great suction power, and the electron is being forced into the nucleus, right? But that's how I visualize it in my head. I have all these visions in my head. But yeah, this is a +1 charge greater than the previous one, right? So for that reason, the nucleus being stronger and having greater attraction power, it doesn't just pull the last electron, it pulls the electron and the whole energy level in. Okay? So the electron gets sucked in just a little closer, and so does that whole energy level. So when I was learning this, okay, I'm going to share what I thought, okay? Disclaimer, what I'm sharing may not work for you. It worked for me and it helped me to recall this because we didn't have no note cards, we didn't have anything, we didn't have internet, we didn't even have a PowerPoint, y'all. And I had to recall all this. So I used to relate it a lot to my life. I was thinking corset. Okay, you know how women wear corsets to suction in their waist so they can have a really, really, really tiny waist. So this is kind of like a not a very good corset because of the +6 sucking in power. This one is a much better corset. And the goal for this is to suck in that electron. So this is after the energy level has been sucked in. It's slightly closer to the nucleus, right? The valence electron got sucked in just a little closer, but not only did the electron get sucked in, so did the whole energy level. So the appearance of the atom is more shrunken. Okay? It's like a tinier waist. Only this is not the waist, this is the whole atom because of the power of the nucleus. Okay? It doesn't just pull in that electron, it pulls in the whole energy level and all the electrons. They're all closer in. Now we're now in oxygen. Same thing happens with oxygen, but even more. So what I'm going to do here, because I don't have a lot of space, this is our inner one and our inner one, and then the next one here is oxygen. So of course I'm going to draw the before real quick before the suctioning happens. Two electrons here. I'll say two here. So our last electron is right here. This is our valence electron. So this valence electron, remember, these are all on the same energy level, right? The valence electrons are all on N2. The inner one is N1. This is N1. This is N1. This outer one is N2. So we are focusing on what is the power of the nucleus to pull in that outer electron and the whole energy level. Oxygen nucleus has even extra, okay? It has +8. So oxygen will be like, so I'm gonna admit, I was watching some YouTube videos of girls training their waist. They call it training your waist, and I was like, effective nuclear charge. Hey, y'all, this is how I think. So they start with a weaker, I guess, a bigger corset, and then as they get better, they move to a smaller corset, and as they get better, they move to an even smaller corset because apparently, as their waist gets smaller, they can handle a more uh, effective corset that cinches your waist even more. They're crazy, but you know what? I watched the videos about it as I'm sitting there eating popcorn, not even caring. It was entertaining. But I use that analogy because for me, it works here that the nucleus is the one doing the job of pulling in the electron, right? So when this is said and done, this nucleus being a lot closer or a lot stronger pulls the electron even more. So now you have the two electrons here. The last one that was here, see, is a lot closer, right? And then the effect that we see in the end is as you go from left to right, the size of the atom gets smaller and smaller and smaller. It's like watching a progress picture of somebody training their waist. It gets smaller and smaller and smaller as the nuclear charge gets bigger. Now, since we're focusing on electrons and not corsets, essentially they're saying here, you're adding the electrons to the same valence shell. You saw me do that, right? In the picture I gave you the example, I was adding the electron to all to energy level 2. These were all energy level 2. And then the effective nuclear charge increases. The nuclear charge is the charge in the nucleus. And when they say it's effective, that's the charge that the outside electron feels as it's being pulled inside. Okay? So the effective nuclear charge is the attraction on the electron is increasing. You can see that from +6 to +7 to +8. Then as a result of that, the valence shell is held closer, which I read as then your waist gets cinched in, right? You go from, yeah, anyway. Yeah. So that analogy for me helped me to understand this. People are like, we don't get it. I'm like, think about corset. What? I'm like, I don't know how to explain this to you. I'll bring the outside world in as much as I can, right? So for me, that explains the logical progression, right? And explains what we're seeing here. So I feel like from the left to right is more complicated. When you go from top to bottom, you don't need all the extra explanation. Here it says atomic radius, when we're going from top to bottom in the periodic table, increases as you go down the group. Since we're talking about garments and clothes and waste, why not stick with that analogy? In this case here, the valence shell is further from the nucleus. Effective nuclear charge is fairly close. So what they're saying here is compare the elements that are in the same group. Okay, so we're done with the left to right comparison. Now we're looking at radius, aka size of atom in group. Okay, so we're looking at the group and we're going down the group. Now in this case here, they tell you that the effective nuclear charge is fairly close. So what I'm going to do here is look at, let me say, in the group, lithium, sodium, potassium. Okay, so lithium, sodium, potassium, when we're going down the group here, I'll show you the most obvious thing. In lithium, sodium, potassium, where is my periodic table? It's easier for me if it's right here. Lithium, I'll write the symbol right here, has a nucleus, and the nucleus based on the number of electrons is +3. And then lithium has how many energy levels? It has 2 energy levels, the inner one, then the outer one. Okay, has 2 electrons here on energy level 1. Energy level 2, it has 1 electron. Let me put it on the bottom here. This is lithium. The next one is sodium. Sodium has what? 11 electrons. It has a nucleus of +11. The first energy level for sodium, oh, that's a horrible circle. First energy level, N is equal to 1, has 2 electrons, right? I'm just drawing the 1 energy level. 1, 2. I should draw this a little to the side. I need more space. This is sodium. Second energy level for sodium. So for this part here, I'm now, if you're wondering where I'm getting those electrons from, I'm just drawing this first energy level. This is N is 1. So let me erase this. If you've had biology, they probably use that model. So this is N is equal to 1. It has 2 electrons, 1, 2, right? Because I should write here 1, 2. And I'm converting the energy level into a circle. Energy level 2, 1, 2, 3, 4, 5, 6, 7, 8, right? And energy level 3, 1, 2, 3, 4, 5, 6, 7, 8. This is energy level 3. So I'm using that to draw the circles, just in case you're wondering. So for sodium, sodium has 11 electrons, right? The first 2 on energy level 1, second 2 on energy level 2. I don't want to complicate it by drawing all the sublevels. That would be very complicated. So 1, 2, sorry, 8 are on the second energy level. 4, 5, 6. Wait, this is 8. And then that makes 10. I have 1 electron on energy level 3, right? Just 1 electron. And this is energy level 3. So this is my sodium. So I'll go through and label so y'all can see which one is the valence electron. For potassium, potassium has, actually, I don't even have to do potassium because I'm running out of room. This is going to get unnecessarily complicated. All I need to do is find the last electron, right? The valence electron. This is my valence electron right here, highlighted. Hopefully you can see that. This is my valence electron. So I'm showing you all 3 electrons in lithium, but I only pointed out the valence electron. This is my valence electron. This right here is also my valence electron. Okay. So the charge by the effective charge experienced by the valence electron, it shows right here. The The electrons in front of it are the ones that block it and influence the effective charge. I won't go into that because I feel like it's going to get too difficult. I'm just going to focus on this. The nucleus that has a charge of plus 11 attracts the electron, right? But it's really not even that simple because the nucleus has a charge of plus 11. But remember, effective nuclear charge is the nuclear charge of plus 11. And then remember, the attraction the electron feels is minimized or is muted by the electrons in front of it. So if you look at the electrons on the energy level 2 and 1, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So even though the nucleus has a charge of plus 11, the electron only feels the valence electrons. Let me write here. Nucleus has a charge of positive 11, but electron only, I use the term feels in parentheses because I'm ascribing human feelings, right? It's really experiences a charge of plus 1. Why only plus 1? Because the 10 inner electrons mute the charge. They don't mute it completely. They kind of encase the nucleus, so only 1 plus 1 charge is experienced. So you have a plus 11, and then you add the effect of 10 electrons, and we end up with a plus 1 charge. That's how we get the effective nuclear charge. Okay, same thing happens here. The nucleus is plus 3. The inner electrons, there's 2 of them. So when you add the effect of the 2 electrons, we get a plus 1. So when they say here the effective charge is the same, where was that? It's fairly close. That's what they were trying to communicate. So if this is not the reason why the size is different, the only reason why the size is different is this one here. Valence shell is further away from the nucleus. So what we're seeing here is the bottom atom, sodium, is bigger or larger than the top atom, lithium, because the valence shell is on energy level 3 versus here the valence shell is an energy level 2. Even though both nuclei end up having a similar suction power, the one on the bottom, sodium, since the valence electron is very far away, it won't move in as much. Okay? So the bottom line, if all this was complicated, bottom line is this. As we go down the group, atomic size or radius increases because valence shell or valence electron, we're going to talk about that, valence electron is on a larger energy level. It's further away from the nucleus. So I can write it that way. On a larger energy level, further from nucleus. So when it comes to garments, it's like saying that you're wearing a lot more garments, so you appear larger. As we go down the group, the atomic size increases because the valence electron is on a larger energy level farther from the nucleus. Okay, so this affects what we see later on. I've already talked about the effective nuclear charge, so I won't go into that part again. You can see right here, they talk about the effective nuclear charge, the charge experienced by the valence electron. Once again, this helps you answer the more complicated questions about effective nuclear charge. For example, right here, we have an effective nuclear charge and the screening effect. So they're asking you, which atom's valence electrons experience a greater effective nuclear charge? So we're looking at the valence electron of magnesium, aluminum, and sulfur. So for this one, essentially what I just worked is what we're going to be doing here. We all know these have valence electrons, but which of the valence electrons is experiencing uh, the highest nuclear charge? So for this, I'm going to draw magnesium, aluminum, and sulfur. Okay, let's look at magnesium, aluminum, and sulfur. So magnesium, where is magnesium? Magnesium has 12 electrons. Aluminum, and this is sulfur, right? Aluminum has 13 electrons, and then sulfur has 16 electrons. So you want to go through and draw your energy levels as circles, okay? So for magnesium, I'll start with my nucleus. My nucleus here is positive 12 based on magnesium symbol, right? Can I draw these side by side? Maybe not. I'm not sure. I need 3 circles for these. Maybe I can. 1, 2, 3. Okay. Each of these need 3 circles, right? Because magnesium is on energy level 3. Aluminum also requires 3 circles. Let me see if I can copy and paste it. That will make my life a lot easier. Can I copy and paste this? Copy, paste. Oh, but I have to change the picture in the middle. This may not work. Oh, snap. It was working until it's not going to work. Okay, it's not going to work. I have to draw it again from scratch. Okay, so I have a nucleus that's positive 13, and I need my 3 energy levels. Energy level 1, energy level 2, energy level 3. Same thing with sulfur. Or maybe I can make these pictures smaller. That might work. Let me try that. Let's see if that works. Okay. And then for sulfur, I also need 3 energy levels. So for sulfur, I have 1, 2, wait, this is 3. These are my 3 energy level. So sulfur's nucleus currently has 16 electrons. Okay. Now they're asking me here, which atom's valence electrons experiences the greatest effective nuclear charge? Now remember I told you how we figure out a nuclear charge, right? The nuclear charge is the charge that the outermost electron experiences after the inner electrons have kind of blocked some of the effect. Let me go over that again in this picture. In this picture right here, they show you how to figure out effective nuclear charge. You have the nucleus here. That is what? Positive 3. So if these electrons here were missing, the outer electron will experience positive 3 nuclear charge from the nucleus, right? But since these electrons are not missing, the outer electron actually experiences only positive 1. Okay? So how does that work out? Okay. Hold on, something